VESEPR stands for valence shell electron pair repulsion, which, along with other factors, produces the molecular shape. LP means lone pair and repels more than the BP, or the bonded pair of electrons. Multiple bonds repel equal to a single bond. The shape name is based on the location of the atoms. The shape of the molecule is determined by minimizing the electron pair repulsions on the central atom. This shape is linear and is represented by AB2. The shape is linear because 180 degrees separates each B. An example of this would be CO2. Two oxygens are on each side of the carbon, or the central atom. This shape is nonpolar because the charges all cancel in the central atom. This shape is trigonoplanar and is represented by AB3. Between two B's are 120 degrees. It is named trigonoplanar because the three B's are on the same plane. An example of this would be NO3. The three oxygens are all on the same plane when bonded to nitrogen. This shape is nonpolar because oxygen, being closer to fluorine, gets the negative charge and nitrogen the positive. Because there are no extra electrons, the charges all cancel in the middle of the nitrogen.
The next shape is tetrahedral, represented by AB4. It's this shape because 109.5 degrees separates each one of the atoms. An example of this is CH4, the C being in the middle and the H surrounding it. There's no lone pairs and there's 4 bonded pairs. This atom is also nonpolar because the positive and the negatives all cancel in the middle. The next shape is trigonoplanar, represented by AB3E, E standing for electrons. It is this shape because it's less than 109.5 degrees in between each one of the angles. There's one lone pair, which you can see at the top, and then there's 3 bonded pairs. This is also a polar atom because of the charges that are unbalanced because of the electrons. Our next example is tetrahedral bent. It's represented by AB2E2, standing for 2 pairs of unbonded electrons. There's also 2 pairs of bonded electrons. A real-life example of this is H2O, and it's less than 109.5 degrees in between each one of the angles. It's also a polar atom because of the screw-up of the electrons and the charges. Our next example is trigonal bipyramid, represented by AB5. It's this angle shape because it's 90 degrees in between this one, and then on the plane it's 120 degrees. There's no lone pairs and there's 5 bonded pairs. A real-life example of this is ClF5, and it's nonpolar because all of the charges cancel. Our next example is seesaw. It's represented by AB4E, which means there is 1 lone pair and then there's 4 bonded pairs. It's less than 90 degrees right here, and it's less than 120 degrees right here. And it's polar because the charges don't cancel like they should because of the electrons. Our next example is the T-shaped. It's represented by AB3E2, standing for 2 pairs of unbonded electrons. It's less than 90 degrees right here, and less than 120 degrees right here. It's polar because of the electrons and the charges are not able to cancel out like they should. Our next example is linear, which is represented by AB2E3. There's 3 pairs of unbonded electrons and 2 pairs of bonded electrons. There's 180 degrees in between the bonded pairs, and it's a polar because of the charges don't cancel because of the electrons. Our next example is octahedral, represented by AB6. There are no lone pairs and there are 6 bonded pairs. It's 90 degrees in between each one of the electron pairs, and it's nonpolar. Our next example is square pyramidal, represented by AB5E. There's 1 lone pair of electrons at the top, and there are 5 bonded pairs. It's less than 90 degrees in between here and 90 degrees in between all of the other ones. It's also a polar molecule. Our last example is square planar, represented by AB4E2. There are 2 lone pairs of electrons, and 4 pairs of bonded electrons, and the electrons cause the bonded pairs to be on their own plane. There is 90 degrees between each one of the things, and it's polar because of the electrons.